In the last video, we came up with this formula. We took the equation for a tangent line to a differentiable function of one variable, and we generalized it. And we came up with this, which I'm calling the candidate for the tangent plane to a function of two variables. And another name for tangent plane would be the local linear approximation. That's also a special name. I'll use those interchangeably. But this function, which will exist provided both partials exist and the function is defined at that point, only earns one of these names if it's a good linear approximation. Now, what do I mean by that? Well, let me remind you of a sort of fun example that we looked at in the last section. We had this function, f of xy, that took points in the xy plane and lifted them to a height of 1, but everything else, so points on the axes and points in quadrants 2, 3, and 4, stayed at a height of 0. So we had this function, which was going to be discontinuous at the origin and along the positive x and y axes. Okay? But when we looked at it, we saw that both of these partial derivatives existed and in fact were equal to 0 at the origin. So for this function, I could build an L of xy. In fact, the function value at p naught at the origin is 0. Both of these are 0. So it would just be the function L of xy equals 0, which is the xy plane. But I don't think the xy plane is tangent to this function at the origin. That's because I don't think anything is tangent to this function at the origin because it's not even continuous there. Okay? So I would say that even though I can build this, it does not earn the name tangent plane or local linear approximation because it's not a good linear approximation. And what I want to try to do in this video is establish what is our criterion for it being a good linear approximation. Now, your textbook and I agree that the definition of a function being differentiable is that there is a good linear approximation for the function at and near the point of tangency. Okay. However, I'm going to present a slightly different definition of differentiability than what's given in your textbook. They are equivalent because they both amount to saying that we have a good linear approximation to the function at that point. And our criterion for being good is the same. We're just expressing it differently. Okay? There is, because my version of things, and I didn't come up with this, our previous textbook used this definition and I preferred it to this one. So when we switched textbooks, I just stayed with it. But because you won't see this definition in the textbook, there is a handout on Canvas that gives you the definition of differentiability that I'm presenting in these video lectures. And that's the definition you will be responsible for using on exams and quizzes. So do be aware of that. That's not in any way, shape, or form to try to discourage you from reading the book's equivalent definition of things. I just think the definition I'm about to present is a little bit more accessible because it really does generalize from what we've got with functions of one variable. Okay, so let's take a look. With a function of one variable, I'm going to again just explore what it means for the tangent line to exist. And I know with functions of one variable, we get that it's a good linear approximation if it exists. If I can find the slope, that's enough to guarantee that it's a good linear approximation. So let's just suppose that I had y equals some function of x, and I'm looking at some point x naught. So there's my point x naught, f of x naught. Okay. And I wanted to try to calculate the derivative, and we will suppose that it exists. So f prime at x naught is just a finite number. As I'm drawing it, looks like it's going to be a negative number. Okay? All right, the way I would calculate that, since this is going to be the slope of my tangent line, of course I just take the limit of the slope of the secant lines. So I would choose a nearby point, x, and of course x could be on either side of x naught. So then we'd have x, f of x is my nearby point, and I can create that secant line. And so f prime of x naught would be the limit as x approaches x naught, so as I move this second point closer and closer to the point of tangency, of the slope of that secant line, which is just f of x minus f of x naught over x minus x naught. Okay, now what I'm going to do is that essentially is my definition of a function being differentiable. If this limit exists and gives me a finite number, then that's the slope of the tangent line. The tangent line exists, my function is differentiable. It has a good linear approximation that we call the tangent line. I'm going to just manipulate this a little bit to see if we can't get a slightly different way of phrasing this. Notice, anytime in math two things are equal to each other, another way of stating that is that the difference between them is equal to 0. So, I could say that 0 is equal to the limit as x approaches x naught of f of x minus f of x naught over x minus x naught minus f prime of x naught. Okay. Of course, if this exists, and this is just a number, I could move this parentheses over to here and let the word limit apply to both terms here. Because if this is just a constant, okay, then the limit of a constant is itself. I'm not saying that the derivative function f prime of x is constant, but I'm saying the derivative at a specific point is a fixed number. It is constant, and so I can actually extend the limit to the whole thing. So I can say this is the limit as x approaches x naught of this entire expression, f of x minus f of x naught over x minus x naught minus f prime of x naught. And what I'd like to do now is just rewrite this. I can write that as a fraction over 1. I'd like to get a common denominator so that I can combine these things. So I'm just going to multiply this by 1 in the form of x minus x naught over itself. Now, when I do that, this becomes equivalent to the equation that 0 is equal to the limit as x approaches x naught of, we're going to have on bottom of one fraction x minus x naught, and on top we're going to have f of x minus f of x naught minus f prime of x naught times x minus x naught. Okay. So that's just doing that multiplication and then combining these into a single fraction. Okay. Now, notice both of these terms are negative. I'm going to just factor out that negative. So this is equivalent to saying that 0 is the limit as x approaches x naught of f of x minus the quantity f of x naught plus f prime of x naught times x minus x naught all over x minus x naught. Okay. Now I've seen this expression in the brackets before. That's my equation for the tangent line, which we were calling L of x. Okay. So what's happening here is I'm going to just draw my tangent line here in red. This is looking, this entire top here is looking at the gap between the y value on the curve and the y value on the line. So it's basically looking at, if I'm over here, it would be looking at this vertical gap between the y value on the curve and the y value on the line. And it's looking at that as a signed distance. In this particular case, the y value on the line at this location is bigger than the y value on the curve, so this would be a negative number that I would have on top. Okay, so this is the signed vertical gap between the line and the curve, and then what I have on the bottom x minus x naught, that's just the signed horizontal distance between these points. Okay. Now, if I look at this, as x approaches x naught, both the top and the bottom of this fraction are going to 0. Of course, we're taking the limit as x goes to x naught. So x minus x naught is definitely going to 0. But as I get closer and closer to the point of tangency, that vertical gap also shrinks to 0 because the line and the curve agree at this point. So this fraction right here is giving me an indeterminate form. The top is going to 0, the bottom is going to 0, but the fact that the limit of the fraction is 0 tells us which is going to 0 faster. In order for this fraction to go to 0, the top has to go to 0 way faster than the bottom. Okay. That way, the top being small wins the argument. The top being small says, I think we should be small. The bottom of a fraction being small says, I think the fraction should be big. If the top goes to 0 way faster, that's a formal mathematical term, way faster than the bottom, then the limit of the fraction will be 0. Okay, so can I generalize that? I think I can. Okay, what I'm going to do is I'm just going to call e of x the function that I have on top, which is just f of x minus L of x. So that's the signed vertical gap. You might say, why didn't I call it g of x? I'm calling it e of x because I'm thinking of it as an error. We're generally going to be using, once we have a local linear approximation, we'll be using it to approximate our function value near the point of tangency. But an approximation is always off by a little bit. This would be the amount that it's off. So I'm using e for error. It's the error we would get if we used the linear approximation to estimate the value of the function. So this is the signed vertical gap between f of x and the tangent line. Okay, so now I want to go back to looking at a function of two variables and see if we can generalize this. I think we're going to be able to generalize it nicely with one slight modification. Okay, so I'm going to define for a function of two variables, I'm going to define e of xy to be f of xy minus L of xy. So that's the signed distance between the z value on the surface and the z value on the, hopefully, tangent plane. So if I have a surface like so, and here's my tangent plane, we're talking about the vertical gap right here between the z value on the surface and the z value on the plane. Okay. All right, and that, of course, is just a difference of two numbers. So that is a signed value. So this is the signed vertical gap, which I can think of as error. If I'm using this to approximate this, this is the error that we're off by. So it's the signed vertical gap between my surface and my plane. Okay. So I can definitely generalize that. That's my generalization of what I have on the top of this. Now on the bottom of this fraction, this is the signed distance between my x values. Signed distance does not generalize in 2 space or in 3 space. Because if I'm in 2 space or 3 space, there are infinitely many directions. I can't use a sign to indicate the direction. Okay? So I can only use signs to indicate directions when I've got just a single number that I'm comparing, not when I'm comparing points in 2 space or 3 space. But I can certainly talk about the distance between points. So I've used this notation before, the distance between p and p naught, which is equivalent to the magnitude of the vector that would have p naught and p as endpoints. So I could use this and it doesn't matter whether the direction of this vector, so I could go from P naught to P, or I could look at P naught instead if I preferred. This is just the distance between P and P naught. Okay. So it's not a perfect generalization of this because this is signed distance. We drop the whole signed thing and just talk about distance between our input points. I will point out, however, that this limit here would be 0 if and only if it would be 0 if I put an absolute value here. Okay. In general, taking the absolute value of things affects them. But if I put an absolute value around part of this, all it could do is change the sign, and 0 is the one number we have that is not signed. Okay. So I've got this nicely defined. So here's my definition of differentiability. Okay. F of P is differentiable at a point P naught in its domain if and only if the limit as P approaches P naught of E of P over the distance between P and P naught is equal to 0. Now, I purposely here switched from writing things in terms of x, y to just generic points, because this is going to work for functions of 3 variables too. Okay. I can visualize what we're talking about when it's a function of 2 variables, but algebraically, this would make sense for functions of 3 variables as well. I'll have to modify my definition for the linear function slightly to take into account that now there's a third rate of change, but I can certainly do that. Okay. So I can then create this vertical gap function. Okay. And of course, as we get closer and closer to the point of tangency, the vertical gap is shrinking to 0. As we get closer and closer to the point of tangency, the distance between my points is shrinking to 0. So this is giving me an indeterminate form. Top and bottom are both going to 0. For the limit of the fraction to be 0, the vertical gap shrinks to 0 way faster than the distance between the points. If that happens, then we can say that our linear function is a good linear approximation, and in that case it earns the name local linear approximation. And of course, if we were talking about a function of 2 variables, that's equivalent to saying it's the tangent plane.